So what we have here is a snapshot of the first 3 periods across the periodic table. When we take a look at each one of these boxes, it gives you a number that's above the symbol. So that'll be a whole number. For hydrogen, it's right here. So these numbers that I'm circling represent a specific property of an element's atom for those particular types of elements. All right? So hydrogen has this 1 above it, and that 1 represents the atomic number. Okay, so that 1 represents the atomic number. So if you look at carbon, it has a 6 above it, and its atomic number would be 6. So what is the atomic number? Okay, the atomic number stands for the number of protons in the element's atom. And it's always going to be a whole number because it's a whole particle that we're talking about. So what that equals is the number of protons a lot of times I'm going to shorten this up and I'm going to put P positive for protons in the atom of an element. Okay? So that's what we have for the atomic number. Now this number that has a decimal, that's down below each one, like for beryllium, it's 9.0122. For lithium, it's 6.944. That gives you kind of an idea of what's called a relative weight. Like hydrogen's relative weight is 1 compared to helium's relative weight that's 4. So if we take a look at hydrogen here, okay, I'm going to get a different screen. So we look at hydrogen here, and we compare it to helium, the atomic number increases by 1. So helium has 2 protons in it, because of this 2, and hydrogen has 1 proton in its atom, right? But if you look underneath, hydrogen has a, what we call a atomic mass unit that's going to be 1, or an average atomic mass, that's going to be 1.008. So that's what we call an atomic mass unit, and that equals 1.008. So they're just relative masses. Okay, we're not going to put a unit with it right now, but we're going to say the atomic mass unit for hydrogen is roughly 1. Okay, if we look at helium, okay, we look at helium, its atomic mass unit is roughly 4. So it's 4.0026. Okay, and what they at the end there for atomic mass unit, they'll put AMU. So A stands for atomic, M stands for mass, and U stands for unit. So if we compare hydrogen atom weight, the average atomic hydrogen's weight, to an average atomic weight for helium, helium is 4 times bigger in mass. Okay? It has double the number of protons. It goes from 1 to 2, but it actually has 4 times the mass overall relative to hydrogen. Okay? We can take another one that kind of goes along those lines. We can take oxygen. And oxygen has 8 protons in its nucleus at atomic number 8. But it also has an atomic mass unit of 16. So if we've got oxygen, it has an atomic mass unit that's going to be roughly 16. So if we compare hydrogen to oxygen, oxygen is 16 times more weight than hydrogen. It takes 16 hydrogens basically, a little less than that, but about 16 hydrogens to make one oxygen's weight. Helium, when we take a look at helium, there's a difference there that helium, you'd have to have 4 helium atoms to make up one oxygen atom. Okay, so that's where that number comes from, and we're going to apply a different unit with those numbers in the future. But for right now, they are relative weights, and you can look at just basically the bigger the number, the bigger the weight the atom would have. All right? The last thing I'm going to talk to you about is this thing called isotopes. And I'll just briefly get into this, and then on class on Friday we'll get more in depth in this idea. So we have this thing called an isotope. Okay, so what's an isotope? Well, an isotope, when you take a look at it, it is an atom of the same element with a different mass. Okay, so when we go up here, there we're going, well, wait a second, don't you think they just have one mass? There's multiple different types of atoms that make up this average. So these are can be called average atomic mass units, and they represent an average of all the particular atoms that are in a sample. So those are averages. So when we take a look at the isotope, we're diving deeper into looking at particular atoms, okay? For example, there's one that we have, that there's 2 isotopes for it, 2 different atoms for the same element. And it's an easy one to look at, it's copper. So how do we differentiate between 2 atoms that have different weights of the same element, okay? Well, what we're going to do is we're going to go ahead and put a number that represents the number of protons, which would be the same for both of those. And that number will go as a superscript, or I'm sorry, a subscript, when we take a look at it. So we're going to go ahead and put the subscripts down for copper, and then copper is element number 29, has 29 protons, so we're going to put 29 down in the lower part. So this here represents the atomic number. So isotopes all have the same atomic number. There's not anything different when we take a look at isotopes for the same element. The atomic number never changes, stays the same. What changes is the mass. But they're different in their weights. So when we take a look at their weights, there's a copper that has a weight similar to 63, and I'm going to tell you what that 63 stands for in a second. And then there's one that has a 65. So these numbers, 63 and 65, they kind of tell us a little bit about their weight differential. Okay, but if you recognize they're a whole number. And so since it's a whole number, it represents a count. So this number 63 is the mass number. Right? And then this 65 for copper, the other isotope, since copper only has 2 isotopes, is the mass number for copper. So what is the mass number? Well, the mass number, definition-wise, the mass number is the number of protons and neutrons in the nucleus. Or the number of protons plus neutrons. I make an N0 for neutrons, so to shorten it up, in the atom. Alright, so that's what the mass number indicates. So the mass number of copper is 63 for that particular isotope. And we also have another isotope with a different mass, but the same number of protons as copper 65. So that's the number of protons and neutrons in the nucleus. All right? If you look at the atomic weight, the average, what we call the average atomic weight, we average these 2 isotopes together. Okay? And they do that, and they come up with an average based upon a percentage each one has. And the average, or which is called the atomic mass unit, is 63.546 AMUs. Okay, so let's just step back and look at this. Okay, so we have 2 different atoms that makes up a sample of a copper compound or copper element that we can look at. If you notice, there's 63 and 65. If you notice, this 63.546 is closer to 63 than it is to 65 when you compare that number representing the weight. So that's going to give you an indication that copper 63 has a higher percentage in the sample. Okay, and then copper 65 is going to have a lower percentage in a sample. And we'll get into that in greater detail. But the main thing we want to talk about and make sure we review is that the atomic number is the number in the upper, above the element, and it represents the number of protons in the atom. Right? Next thing we can look at is atomic mass unit is the number that has a decimal, and that's their weight comparison, their atomic mass unit relative weights compared to one another. And then the last thing that we talked about is showed you what an isotope looks like. An isotope can be written with the symbol, and then down below, subscript, is the atomic number. It'll always be given to you. And then up above is the mass number. Now, you're not going to be able to find that on the periodic table. That'll be given to you. And that represents the mass number, which is the number of protons and neutrons in an atom. So then what we're going to do tomorrow is we're going to work through doing some problems with isotopes so that you can look at more things other than protons and mass number in an atom.